Hello, everyone. My name is Henry Bright, and I'm going to be going through Project 2 for EAS3810 with Professor Osbey. Basically, we're going to be doing an external flow simulation within the wind tunnel that we designed in the first project, two-dimensional wind tunnel. So you can see we get these four objects. We're going to place each one inside the wind tunnel and kind of test some of the properties. So you can see we'll be using the 50 Hertz case, so I'll go over the velocity inlet for that. And need to size these to make sure that we mitigate blockage effects. We could do any NACA airfoil, so I'll go over that as well. In the next video, I'm going to do a second video doing the airfoil. This first video is just going to be doing, I'm going to pick one of the objects. I'm going to do the number 2, so the hemisphere with the flat edge as the leading edge. And we're going to get static pressure, velocity. We'll look at the contours for those, and then streamline patterns as well for velocity. And then we'll get the drag force as well as the drag force coefficient. So I'll kind of go over how to do that, but just for this particular shape. So let's go ahead and get into it. So we start with our workbench. I'm going to go ahead and start. Here's opening our design modeler. I'm going to go ahead and start with the wind tunnel already created in here. I'll be dropping the link in the description for my video for project 1, so you can kind of see how I made this this wind tunnel. It's the same thing. So I just went ahead and loaded it in here to save time. So to go ahead and make this shape, first to start off, we'll go ahead and zoom in. And the first thing we got to do is draw a circle. So we'll draw a circle starting from the origin. Doesn't matter right now. Go ahead and create it, and then we're going to dimension it. So back to what I said about the blockage effects, we need to make sure that in 3 dimensions that the frontal cross-sectional area of this object divided by the frontal or the cross-sectional area of the wind tunnel has to be no more than 10%. Sometimes it was here 7.5%. I went ahead and used 10 for this project just to make the object slightly bigger. So there might be a little bit of blockage effects if my ratio is a little off, but that's the number that I've been going with, somewhere around that. So anyway, the height of our test section, if you remember, was 6 inches. So that's going to be 0.1524 meters. So we need to do 1/10 of that basically, because in 2 dimensions, we'll just basically use the ratio of heights, because span would be basically the same. So we'll go with 0.01524 meters. Go ahead and mention that. Awesome. So the next thing I'm going to do is I'm going to go ahead and draw a line that cuts through the cylinder. Doesn't matter where initially, because then we'll constrain it, make it vertical, and then we just got to dimension it. Dimension it, and we're going to want that dimension E27 to be our 0.01524 so that it goes to the center, just like that. And then the last thing is to make it a hemisphere or like a semi-cylinder, half cylinder. Forget what I'm saying. We're going to go ahead and trim this. So if I just go ahead and trim on that front edge, it's going to trim it by axis. It's paying attention to the axis there. So now we have our half cylinder. Easy as that. Beautiful. So I'll zoom back out. You can see the whole thing. It's very small, obviously, within the scope of the size of the test section. But the next thing we'll do is just do what we normally did in the last project. We'll go ahead and do concept surface from sketches. And if I go ahead and box select all of it and hit apply, and then we'll have to hit generate. Oops. Oops. Here we go. Sorry about that. Gonna move around everything on Zoom. All right, beautiful. So now we have surface from sketches created, and you can see our object is right there. And that is perfect. So that's the first step for this project. So we got that done. So we'll go ahead and come in here and update our geometry. And then we can open up our mesh. And basically everything else here is going to be the same as before. The only thing that's going to be new is we're going to have to update our name selections first of all. And when we do that, we're going to have to create a new named selection, which is going to represent the wall of our object in the middle, because we'll need to use that for getting some of the properties like the drag force on the object. So this is re-updating. Hold on a second. There we go. Now we've got our correct object. I had done the airfoil before in this. This was the same project that I had used for that on Fluent. Anyway, so to update our mesh, you can see it's there. We've already got our all triangles method. Remember that from last time. The only thing is now I need to add it to this new geometry. So I go ahead and hit apply, and that's perfect. We'll keep the same element size, and we'll go ahead and generate our mesh as before. So we'll wait just a second for that to happen. And then, like I said, I'll also go about updating those named selections so that we have all of those. That's going to be very relevant for getting our solution. So we'll just hang tight here for a second. And look at that, looks beautiful. We'll zoom in just so you can see. There you go, meshed right around the object. A little hemisphere in 2 dimensions. Awesome. So now we go to name selections, and you can see I've already got the ones that we had previously updated, but you can see the X through here. That means they don't have a geometry selection, which you can see here. So I'll go to edge select, and then go ahead and hit this one for velocity inlet, hit apply. And now we've got our velocity inlet. You can see it's checked off now. Do the same thing for pressure outlet. Boom. And wind tunnel wall is going to be the same as before. You'll have to hit control while you select all of these. So it's going to be the, 8 of them, I think. Form the wall. 8 edges, beautiful. And then the last thing, I have this listed as flat plate wall. I kind of was a misnomer from the very beginning when I did it. I just haven't bothered to change the name of it. It really doesn't matter. You know what it is. But it's going to be because I did it for the flat plate case. But it's just going to be the wall of our objects, in this case of our cylinder. So if we're going to select the geometry, we'll need both these edges. So again, control, so you make sure you get both of them. There's the 2 edges, and that is our flat plate wall. So that is all fine and dandy. So we'll come back to our workbench and go ahead and update our mesh. Awesome. So now we can go into the setup. You'll get lots of pop-ups here. This will be the same as before. We'll stick with double precision, 2 solver processes, and we'll go ahead and open this up. Again, this is going to be basically very similar to what we've done before with the wind tunnel. One thing I will touch on, I'll actually open my data sheet here, is we needed to use the 50 hertz case. So I had the velocity, we need the test section velocity of about 12. And so hypothetically, using our height ratios, we have a velocity. It didn't work. I already went through the process of kind of guess and check, trying to get the right velocity to get that test section velocity. And the actual one that I got was 2.53 meters per second. So that's what I'm going to use for all of these cases to get that, just for consistency purpose. And that should give us about a free stream velocity of about what we want in the test section. So it's just a little side note there. All right, looks like everything's loaded in. So same thing as before. Major things you need to do, you use your model. I have the energy on. I did the standard K epsilon with the enhanced well treatment, all that fun stuff from the last video. I can pull that up just to show you. Yep, you can see that is the same. And then the next thing we need is boundary conditions. So you have your inlet. This is where you put in the velocity that I was just talking about from my document sheet, the 2.53 meters per second. Beautiful. And then other boundary conditions, you have like your wall, and you have your outlet. So we're going to, again, gauge pressure is going to be 0. That's going to be our condition again. I'll show you that. Just make sure we cover all our bases. Yep, exactly what we want. And then you can see it's already generated both the both of the walls, and they're just stationary walls, so that's easy enough. And so then we can go ahead and move on to initializing. Again, very much the same as the last video. I probably shouldn't even be going through this because it's something we've already done. But I'm just doing it just to cover all the bases. So then we'll go ahead and hit calculate and we wait. And then once that's calculated, you'll see our residuals popping up here for a second. Once that's calculated, then we'll go ahead and go into getting some of our data. So basically what we're going to look at is we're going to look at the graphics like before. We'll get the contours. So we'll do velocity contour as well as static pressure contour. We'll take a look at that. We'll zoom in on the object to see what that's supposed to look like. And then we'll also, one thing that's new is we're going to get the drag force on the object. So we're going to use our reports section on the results side here. And there will be a force report that we can get under a console. And basically that will tell us what the drag force is. It'll break it down into pressure drag and viscous drag or skin friction drag. And we'll kind of be able to see if our results make physical sense based on what the objects are. So in this case, with the half cylinder, with the leading edge being like that vertical edge, we're probably going to expect a decent bit of pressure drag just because it's kind of hitting, it's kind of a bluff body. So we'll probably see a good bit of that, kind of similar to the vertical flat plate. But who knows? We'll see. Don't want to give away too many spoilers. Yeah, so we'll continue to wait on this. We're almost done. Awesome. So there it is. All right, now let's go ahead and get into it. So we got our graphics. We'll do static pressure first. Go ahead and select all of these, save and display. And look at that. Static pressure, you can see it's kind of continuous in the vertical direction for the most part. In the rest of the wind tunnel, you can see it decreases going to the test section where it kind of reaches the minimum. And then if we go ahead and zoom in on our object, you can see some interesting things already. Look at this. So this is exactly what we would expect. So you've got this high pressure region that forms at the front of the body. And then at the back, you get this really big wake region where the pressure is a lot lower. That's actually one of our lowest pressures you can see using the color that's generated. But basically that's going to create that drag force because you're going to have flow wanting to go from the high pressure region to the low pressure region, and flow's going this way. So it's going to be basically resisting the motion of the object. The object, we're like flying from right to left. That's going to be that drag force. So that looks like exactly what we would have expected. Now let's take a look at our velocity contour. We'll also again be looking at the streamline patterns. So this is kind of going to be a little repetitive, but you can see again, same sort of thing. You have your lower velocity at the inlet. You can see it continue to speed up. You can see your no slip condition along the walls, but you see it speed up going to the test section, reach kind of the maximum velocity there. And then if we go and zoom in on our object, you're going to see kind of like the opposite sort of pattern as static pressure, where you've got that wake region, like I told you about, kind of forming behind the object. We've got a lower velocity, could even potentially get some flow separation. We might even be able to see that in the streamline patterns, not to spoil anything too soon, but we will see. Yeah, this is exactly what we'd have expected for our object. And that's kind of how the velocity contour looks. And then before I navigate away from this section, I'm going to show you the force report. So if you go down to reports and forces, go ahead and double click on that. You want your direction vector x1, y0, because that's going to be in the x direction. That's where our drag force is going to be. And in this case, you just want to select flat plate wall, or in this case, it's the cylinder or half cylinder, whatever you want to call it. So we just want that flat plate wall. So we'll go ahead and print it, and it goes ahead and prints it up here. Super nice. So you can see basically almost solely the pressure drag. So it breaks it down to the pressure drag, viscous drag, and then total. So you can see it's basically completely pressure drag. There's some slight error here where you can see there's actually some negative viscous drag. that might even have to do some with that flow separation. There might be some force from the velocity kind of like circling back on the back edge of the cylinder and kind of pushing in the direction, um, in the motion direction of the object. So that could be an explanation for that. Otherwise, I'm not sure. It might just be a slight error in the simulation. But you can see then you've got your drag force total. And then you can see it gives us other coefficients, but we're actually going to calculate those by hand. I'm not going to show that calculation, but literally all it is the drag coefficient is just equal to the force of drag divided by the dynamic pressure in the test section, or like, around the object. So we would just use like the calculated one we got. It might be a little off here because you can see that, our max velocity and our velocity is very variant around the object, depending on where you're at in the test section. It's a little bit off. But we're going to just use the calculated test section velocity for that dynamic pressure. And then that will be multiplied by the diameter of the cylinder. That's like the critical length. So basically it's going to be a drag coefficient per unit span, since we're just in 2 dimensions. But that's how we're going to do it. We're going to actually do it by hand, but you'll want these drag force numbers that you calculate, mainly the total drag force. Okay, and so the only last thing I need to show you is we'll open up the results menu to get the streamline patterns. This is pretty easy. There's a lot of different things you can actually look at in the results tab, but we're just going to be looking at this one in particular. I think because I've ran this already, it'll probably go ahead and generate once we get loaded up here. But I'll show you kind of how to do it. Yeah, there you go. So you can see that's already what it looks like. So basically what you would do from scratch is you would want to insert the streamline. So you can see name streamline 2. I'm not going to go ahead and actually do it. But yeah, you would have this. You do the surface streamline. You would click the surface. You'd want the, you would want to do the symmetry 1, I believe. It might be symmetry 2. I can't remember. And then just increase your number of points. I think I did 200 for mine. Let's see. Yeah, okay. Here, so symmetry 2, yes, 200 points is what I did. You could do even more. It's just going to take a little longer, but it'll give you slightly better results. And yeah, so then you'll get something that'll look like this. And if we go ahead and zoom in on this within the test section, kind of around the object, there you go. Look at all that flow reversal, flow separation. Not good. Makes sense because it's more of a bluff body, but you can see, the velocity is accelerating around, reaches like some stagnation point in front of the object, and then you can see like behind it there's this massive wake region with some reversal going on, and that's contributing heavily to that pressure drag that we've been talking about. But these results make exact sense for what we'd expect, and honestly I think that's it for this part of the project. I'll be uploading a part 2 for this video to show you how to do the same sort of thing, but with the airfoil. So stay tuned for that. Thanks.